Okay, so looks like that's working. We're going to start on 5.4 today, which is conditional probability and the general multiplication rule. Okay? All right, so we're going to talk about conditional probability. And that's written as, well, we can think of it, it's written as the probability of F given E. So that's just a kind of a straight line. So that's read as the probability of event F given E. Okay? So let's pretend, for example, I've got this little cap here. We're going to pretend this is a die. So I'm going to shake it up in my hand. I'm going to look at it, and I'm going to say it's an odd number. Okay? So given that this is an odd number, what is the probability that it's 3 given it's an odd number? 1/3. You guys figured that out. So the idea with conditional probability, I give you some conditions. Now, if I hadn't given you any conditions, what would it have been? A probability of a 3 with no conditions would be 1/6. Okay? So I've improved my chances of picking correctly because I've gotten more information, right? So that's the idea. So the conditional probability, one of the things you can think about is it shrinks your sample space. Because now my probability or my sample space is simply 1, a 3, or a 5. Okay? Does that make sense? Okay? All right, so let's go back to that spreadsheet we had open yesterday. If we go to Canvas, let me start sharing. And assignments, and in class worksheets, 5.2. Okay, there was a few questions that were on there yesterday that we didn't answer. I'm opening up a blank sheet, so go to the two-way tables. Okay, so I probably should go ahead. Oh, it's not pulling up because I'm sharing on this video, but not on the class. Okay, so I'm just going to go ahead and get the totals again. All right. So we figured all these out yesterday, but since I opened the blank sheet, we don't have those answers. But what would be the probability that someone is widowed given that they are female? Must be Ashley's turn. So given, what have we shrunk our sample size to? So we're only looking at the females now. Okay, so I'm going to highlight in that yellow. And now, what's the probability that they're female, that they're widowed? So 2.6, how did you get that? 11.3. So we're really, I'll put that in a different color. So we're really looking at that color there. So the probability that they are widowed given that they are female, how would I figure that out? 11.3 divided by 113. So almost 10%. Does that make sense? Okay, so what is the probability that a random male has never married? Okay, so this one doesn't quite have the bar there like that one did, but it is a conditional probability because what are we looking at only now? We're only looking at the males. So we're looking at the males. So we'll go blue, I guess. And so Chris, it must be your turn. A random male has never married. What am I looking at in the male column? 30.3, so I'll put that in, say, I don't want to do yellow, brown, okay? So this would be
about 29%.
Okay, how'd you get that? You're supposed to tell me. Not do it. So 30.3 divided by 6.2, that works out to be about 28.5%. All right, what's the probability that a never married is male? How would you figure that one out? Must be Trevin's turn. Okay, so we're looking at this line here. Okay, so now I'll pick what color? Purple. Okay, and we're picking a never married is male, so we want that number again. I'll go back to brown. Okay, so this is what again? 30.3 divided by 55. 54.8. Okay. Piece of cake. Can I ace my test tomorrow? All right. Okay, let's talk a little bit about, we'll go back to the board here. All right. Let's talk about the conditional probability rule. Okay, so that says the probability of F given E equals the probability of E and F divided by the probability of E. Okay, now I know that my notes are off a little bit, so I'm going to go to the book to make sure I write this down right, because this one always gets confusing to students and I need to fix my notes. All right. All right, what if I told you that in 2007, 12.7% of births were preterm, meaning less than 37 weeks. Okay? And I also told you that in 2007, 0.22% of all births were, let's see, of all results returned to a preterm baby that weighed, here I'm going to say, greater than 8 pounds, 13 ounces, which we're going to call overweight. Okay. So find the probability that a random baby was overweight given that they were preterm. Okay?
What is the weight in pounds?
What'd you say? 8 pounds, 13 ounces, we're calling that overweight. Oh no, it's greater than 8 pounds. 78 pounds would be a very large baby.
That's what I was like.
Yeah, that would be like an elephant baby or something, I don't know. Okay, so we're going to use our conditional probability rule here. We're trying to find this. We want to know the probability of E and F. So 0.2% of all births are preterm and, I guess maybe I'll put an and there, weighed greater than 8 pounds, 13 ounces. Okay, so that's going to be 0.22 on the top. On the bottom, we want to know the probability that they're preterm, which is simply 0.127. Oh, actually, this is 0.0022. I need to convert that to a decimal. Okay, does that make sense? All right, so when I plug that in, I should get an answer of, oops, my numbers all match, 0.0173 or 1.73% of all babies are overweight given that they are preterm. Does that make sense? Okay. I guess my notes were right this time. All right. Now, what if I solved this? Okay, if I did just a little bit of algebra, I could multiply both sides by the probability of E, right? When I do that, that becomes the general multiplication rule, which says that the probability of E times the probability of F given E equals the probability of E and F. Okay? All right. So let's do a different example. This example says the probability that a driver is speeding and gets a ticket equals 0.8. Okay? Let's say that the probability that the driver gets a ticket, given that they were speeding, equals 0.9. What is the probability that a driver is speeding and gets a ticket? You can think of those as percentages, yes. Okay? So, what do you guys think? All we're going to do is we're going to plug it into here, right? This is the and. It's the and is what I want. So this is the F, this is the E. So therefore that must be the E. You can plug it right into here, okay? So I'm going to get 0.8 times 0.9 equals 0.72. Matches the general multiplication rule right there, okay? All right. Okay, let's do another example. It seems really bright today. I don't know why, but all right. So let's say, yeah, the video looks really bright. I don't know why. It's like
Maybe it's because you're wearing darker shirt than normal today. Just like the contrast.
I had blue yesterday. Remember my Bennett College? Did you guys know that Bennett College is really a college in North Carolina? It's a black women's college, dates from the Civil War. I'm definitely demographic for that. Okay? We've got like 600 students. I saw it on my way to Wake Forest one day. I was like, I got to get me a shirt. Anyway, all right. So, example here. We've got 100 circuits are shipped and 5 are defectives. Of course, you don't know that when you're doing that, but let's say that that's really what happened. Okay? All right, so the receiving manager selects 2 and tests. If both work, she accepts entire shipment. Okay. Find the probability of at least one defect. Okay. So let's think about this for a minute. Sample space can be very helpful. At least one means what, Chuck? Okay, we could call them good or we could call them bad, right? So G and B. Let's use G and B for good and bad. What's your sample space for at least one bad?
Something to do with an inverse. It's the you find all the.
Here, let's just list all the you only got 2 of them, right? Let's just list all the possibilities. Where are all the possibilities?
Yeah. It's all possibilities. It should be either good or bad.
So no, you're only testing 2.
Oh, you're only testing 2, right? So it'd be good, good, bad, bad.
Good, good, bad, bad. Good, bad, bad, good. Okay? So at least one defect would be these 3, right? Do you agree with that? Okay? So what's the easiest way to do this?
Just test the possibility that the first one she picks is a defect.
Well, there's 2 ways. I can do all 3 of these, right? Or I could do 1 minus the probability of good, good, right? That would actually be easier, wouldn't it? Okay, so let's think about that. What's the probability that the first one is good? It's 95 out of 100, right? What's the probability that the second one is good? 94 out of 99. Okay, and that works out to be 0.098 if you do the math. So the probability that she finds at least one defective is about 10% chance. Okay? We're doing pretty good on time today. We could do this with a tree diagram. Would you want to do that? Especially since you need practice with your tree diagrams.
So, times those together.
Yes. Is that not right?
No, that's right. Sorry, I just put 99 for the first one.
Okay. All right. So another way to do this, because I know you guys love tree diagrams, let's think about this again. Okay. One way to do this, especially since I got an extra minute, is you're going to pick one. It's either going to be good or it's going to be bad. And then you're going to pick a second one, and it's going to be good or it's going to be bad, or it's going to be good or it's going to be bad. Okay? Now, probability that the first one is good is 95 out of 100. Probability it's bad is 5 out of 100, right? The probability that the second one is good, now by the way, are these independent or dependent probabilities? These are dependent, right? Okay, because once you've tested one, well, theoretically you could stop, but we're trying to do this the whole way, okay? So the second good one would be 94 out of 100. No, not out of 99 now, right? Because we've already tested the good one. And this will be 5 out of 99. This one here, if the first one is bad, the second one is good, has a chance 95 out of 99. The second one being bad is 4 out of 99, okay? So you could do that as well. I could go if bad, bad. I could go bad, good. I could go good, bad. I could add all those up together too. So another way of doing this would be probability of good, bad. In this case equals 95 out of 100 times 5 out of 99. I could go, try to make my colors match here. I could go probability of bad, good, which would be 5 out of 100 times 95 out of 99. Or I could also go back to my purple here, probability of bad, bad is 5 out of 100 times 4 out of 99. At any rate, I could simply add those together. I should get 0.098 as well. Okay, so that's how you could do it with a tree diagram. Okay. All right, let's do another example here. Oh, did I move my camera? I didn't, but here, we'll go over here. Now you can see the board, maybe. There's your tree diagram. Okay. All right, so now let's go with, let's say that we did a survey of 10,000 African Americans, found 27 had sickle cell anemia. Okay. So the first question is, what is, excuse me, what is the probability that an African American has sickle cell anemia? Let's pick on, it must be Samantha's turn. I didn't get to pick on you yesterday. Okay, what do you think? Yep, 27 out of 10,000. Okay. All right, so now what is the probability of 2 African Americans with sickle cell anemia? Okay, I want to do this two different ways, with replacement and without replacement. Okay, so it must be Tanner's turn. If we assume with replacement, so we pick somebody, we stick them right back in, and we could pick them again. Okay, so what's the probability that the first person has sickle cell anemia? I can't hear you. There's only one person that has it? I thought there were 27. The probability that I pick one person that has sickle cell anemia, the probability that happens is it's the same answer we just got right there. Do you see that? Okay, so it's 27 out of 10,000. Okay, now we put him back in the crowd. There's a chance we could pick him again, but what's the probability that we pick a second person with sickle cell anemia? The same thing. And what do I do with these two numbers? Multiply them, okay? So if I multiply those together, I get 0.8 Yeah, let's see here. I got 1, 2, 3, 4, 5 zeros. 1, 2, 3, 4, 5 zeros. And then I get a 7, 2, 9. Okay, let's do the same thing again. But this time we're going to do it without replacement. So, Tyler, what's the probability the first person that has sickle cell anemia? 27 over 10,000. What's the probability that the second person has sickle cell? I should have picked on your Russell, huh?
26
Over 999, whatever. And that works out to be also 1, 2, 3, 4, 5, 702. Okay? So as we look at these two numbers here, okay, look, to 6 decimals, they are exactly the same. Okay? So those are so close. Does it really matter whether I do replacement or not? Okay? I mean, technically it does. Technically this is dependent, right? This assumes independence, this assumes dependence. Okay? So here's what I mean. So in practicality, we like independence, don't we? Okay, independence makes our life easier. So with large samples, it is reasonable to assume independence. Okay? Now, when you say large, what is large? Okay? As a rule of thumb, your sample must be less than 5% of your population size. Okay? Now, if I were doing something in this class only has 30 people in it. I think 29, can't remember. Anyway, let's say 30. If I wanted to do a sample size of 10 people and find out if you had sickle cell anemia or something like that, could I assume independence? No, because 10 divided by 30 is 33%. That's more than 5% of my population. But it's also why when we do these, when they do these polls and they only talk to 1,000 people and you've got 100 million Americans, it's why you can get away with 1,000 people, okay? So the last thing I want to just let you know, we've got conditional probability rule and independence. And what that says is if the probability of E given F equals the probability of E, and the probability of F given E equals the probability of F, it is okay to assume independence. Okay? So essentially, you remember when we said here, when you're doing conditional probability, you're shrinking the sample space. Well, if the probability, so let's think about this. If I said in this class, I think we've got 4 women, so the probability that a random person in this class is 4 out of 30, okay? What if I said, what's the probability that you pick a woman given that the person is wearing purple shoes? Does the purple shoes have anything to do with whether you pick a woman? Maybe, but probably not, right? So this F really doesn't add anything. It doesn't really shrink your sample space. Okay? So basically, if I know E and I give you some other thing F and it doesn't change the probability, then E and F are independent. Okay? All right, so just a reminder, test is tomorrow. Written will be in here in class. It will not be as short as the last one. Okay? Last one was way too short. Hopefully it won't be too long. What's that? Well, we'll plan on the hour. So.